about to begin the material for chapters 5, 6, and 7. In our CATS text, she breaks it up a little bit, and it gives you an introduction to Newton's laws in chapter 5, gives you some applications of Newton's laws in chapter 6, and then brings it all together with a chapter 7 titled Gravity. But I like to teach all three of these chapters together, so we're going to pull it all together in this one overall PowerPoint/video. So I'm going to give you an introduction into Newton's laws, their application, and how it applies to the universal law of gravity. Since this is part of our new course format, I want to point out a couple of key resources. You have a number of things in Blackboard that's really going to help you out. You may want to just stop this recording right away and go to the Cool Videos section and go look at the two Veritasium videos found in the Cool Forces videos, which is in that section 2 folder in Blackboard. And I really want you to kind of think about it because they go into what is a force and the forces that are acting on you at any given time. And they do it in kind of a fun, lighthearted way so that you can kind of see some real world applications. Then I want you, if you want, you can go to the source and check out the following, the Newton Project. Now, I always bring this up because one of the things that we as engineering students or as science students are always looking at are our notebooks. And notebooks are incredibly important because it's going to convey information about the studies that you've been doing, plus recording all that scientific information as you go on. And I like to point this out that you never know who's going to be looking at your notebooks, so you want to really think about how that notebook is going to be handled, because this is the source, the Newton Project. The Newton Project has recorded all of Newton's papers, and you can actually still go back and look at Newton's notebooks. These are the notebooks that he used to do a lot of the information that we have, that we're going to see in later on and how these apply. Then if you need help with free body diagrams, you can check out the physics classroom, because free body diagrams are going to be essential in getting and working these projects or problems throughout this chapter and in chapters going forward. As I've said before, always draw your diagram because your diagram is really, really going to help you out. Well, now that we're dealing with forces, we need to see those forces applied on the diagram, and we're going to cover that a little bit. And of course, check out the other videos in the Cool Videos. Make sure that you're keeping up with your text. So let's start out with what is a force. Well, simply, a force is a push or a pull. And you can see my other historic lecture dealing with that push or a pull, but we know that if I have a rock, I'm going to have to apply a force to get that rock moving, or I'm going to have to pull to get that force moving. So there's a lot of ways that we're going to look at it. And one of the things that we want to deal with that force is we know that the bigger the rock, or the more mass that the rock has, the bigger the push or the pull that I'm going to have to do in order to get that mass moving. We know this intuitively. We've played with this since we were little kids. So we know that we have to deal with that push or that pull to get us there. So let's think about that concept of mass. Back in chapter 1, we kind of talked about it a little bit. Mass is stuff. And it doesn't matter, my mass isn't going to change when I go to the moon, or if I'm sitting on Saturn, or if I'm sitting in the sun. My mass isn't going to change. That amount of the mass is not changing. It relates to the stuff that we have. A key point here, mass is not equal to weight. Weight is how gravity is affecting that mass. So I have a different weight if I go to the moon, if I'm sitting on Saturn, or if I'm sitting on Mercury. I'm going to have a different weight relative to that mass. And we know that, and we've seen it, and we've played with it before. So weight is going to be my mass times the acceleration due to gravity. And we're going to cover that in a little bit. But let's go back to that rock where we're doing that push or that pull. And we know that the more mass that's in that rock, the more force that I'm going to have to apply in order to get that mass to move. Okay? This gives us Newton's first postulate. And let's kind of think about it as a thought experiment first, because ultimately this becomes Newton's first law. But that first postulate is, and he's sitting there pondering, going, okay, let's think about how mass and force are related. Okay, I I know that if I have a more mass, I have to apply a bigger force. And so this comes, what he's saying is that every body, an object, an item, a particle, continues in its state of rest or in its uniform motion in a straight line unless acted upon by a force. So think about that screwdriver that's in the space station. The astronaut's going to toss that screwdriver. It's going to go in a straight line according to its constant velocity until it hits the wall of the space station. So another force has to act upon it. If you think about a hockey puck is in a pretty frictionless system. Once the force is applied, the hockey puck is going to go off in a straight line at a constant velocity until what happens? It's either hit by another stick or it hits the wall. So Newton's first law is saying that object's going to sit there at rest. It's not going to move unless I'm going to get a net force applied to it. Now, we know that the wall, that there's forces on a wall. I can go and push on the wall all I want to, and it's not necessarily going to move for a couple of reasons. One, I may not be applying enough force based on its mass. The other is that there are other forces holding that wall in place, and I can't apply a net force to that wall. So we know that we're going to have to see a little bit of difference. So let's go back to let's take for a second and let's go back to that object in motion remains in motion unless acted upon by a force. So when we dealt with our projectile motion problem, we had a situation here where I had the ball that was going up and traveling in the y direction, and I had a ball that was going in the x direction, and in the x direction it was traveling at a constant velocity. Why? Because there was no additional force being acted upon it. Now if I'm in the y direction, because we've played with gravity since we were little kids, the gravity game, dropsy gravity game, that dropsy game, when we have the ball in the y direction, I have a force due to gravity that's pulling on that ball. So I do get a change in motion. It does experience an acceleration. Okay, it does have that acceleration, and we get that change. So we know that unless I'm acting on that object with some sort of net force, it's going to sit there. And that gets us back to this other idea of mass. Mass is related to inertia. So let's look at this for a second in a real world situation. So I'm going to run this little video real quick.
About physics is that you can do a variety of experiments even on your desktop. I'm using my phone to video my little laboratory device. It's called an I/O lab. It has certain features on it. It's got something that's going to orient our accelerometer, and we're going to be in the y direction, even though we're going to go back and forth on the table, but that's the way the accelerometer is set up in this particular one. It has 3 wheels on the device, and that will help us measure things like velocity and time, and measure distance, measure acceleration, and I have a force sensor on the device. Here's my force sensor, and I can look at the force associated with it, and I can look at the push and the pull. And that's what what we want to look at here is we want to look at that motion, and we want to look at the force that's being applied. Now, it is connected using a USB connector to my other computer, and I can actually collect real-time data. So I'm going to set this device here. We're going to actually pull it up and down our meter stick so that you can actually see the motion. I'm going to start the recording on the computer, so we're actually going to see this in real time. And I'm going to actually start and hit record. So this motion is going to actually be real time. I'm going to pull on the force sensor, and I'm going to move it up the meter stick, and I'm going to move it down the meter stick. And of course I'm registering it on the force sensor, so I'm moving it up and I'm moving it down on the meter stick. And I've actually collected some real-time data on our system with the USB port. So I'm going to stop this right now. I'm also going to stop the recording there, but I want to be able to put this together so that you can see the motion and the force. And once I do that, we'll have a bigger discussion.
So now let's go ahead and have that discussion. So here was the force that was being applied. Now once we apply, until that force was applied, the little I/O lab didn't move. It didn't move. It didn't go anywhere. And once it started moving, we started seeing that change in position. We got a velocity, and you'll see that there's a little bit of an acceleration. That acceleration is what's causing our motion in this case. And as the force was applied, we changed our position, we changed our velocity, we even had a change in velocity. Again, that change in velocity is showing that we have an acceleration. And so we can utilize that postulate that Newton said, an object in motion remains in motion unless acted upon by a force. We had a force here that caused a change in the motion, and that would allow us to actually see something that's going on. So we know that we're going to actually work with that, and it comes back to
about physics.
our acceleration. So let's think of another example. We have a nonstick pan here, and that nonstick pan has an omelet in it, and if I jerk that pan, the omelet is going to go to one side of the pan. And that's because the omelet's on a very frictionless surface here. There's nothing that's holding those eggs in that spot. So there's not being a force really being applied on the eggs until the edge of the pan hits it. And then we get a force that has those eggs move. So the force is the pull on the pan. The egg is going to want to stay where it's at. It's not going to change its motion until a force is actually being applied to the egg. And so we're not going to see that change in motion. Think about when you're in your car. If I didn't have a seatbelt on when I slammed on the brakes, what's going to happen? I'm going to continue to move forward. Or an object in the seat's going to continue to move forward, because an object in motion remains in motion unless acted upon by a force. So we've seen the example of a tool in the space station. We've used that example of the car. But one of the things that's about that going back to that change in mass, the bigger the mass, the more inertia that the object's going to have. And we're going to see that when we look at Newton's second postulate. We're going to see where that mass comes from, but I'm going to get that, and that inertia is related to the motion, and we're going to have, and the definition of inertia is the resistance to motion. Okay? The more mass it has, the more resistance to motion it's going to have. I'm going to have more inertia that's going to be, or a change in motion that I'm going to have to deal with. So we've got that part there. So at this point, it's really a good idea to talk about two types of forces. We kind of know about those two types of forces, but we probably have never really put it together. We have a force that's a contact force, okay? I'm pushing on the wall, or here we have Mark pushing against Wilma. They're actually physically in contact with each other, and the two forces are being applied. She's applying a force back on Mark. Mark's applying force back on her, and we know that we have those forces. And we're going to see that this is also an example of Newton's third postulate, where once he's applying a force and she's applying a force back, we've got those forces, but they're in direct contact with each other, and those are called contact forces. That force due to gravity that we talk about, the dropsy game, that dropsy game is related to a field force. Gravity is acting on the mass. It's pulling it towards the center of mass of that object. And so we're actually getting that mass. You also see the GIF here that's showing the bowling ball and the feather in a vacuum. And we've got that force due to gravity pulling on those two objects that are pulling them down towards the surface of the earth. And I've got that video is also in the Cool Forces videos. So we have two types of forces, a contact force and a field force. And that's going to come important later on. So let's go to Newton's second postulate. His second postulate, what he actually says, and I like to bring this in. You aren't going to see this in your text, but I like to bring that in right now because everybody sits there and thinks Newton's second law, you could probably put it up there right away. But that's not really what Newton said. And that's really what's important here is because as we go further into mechanics and we go further into our junior and senior level classes, you need to understand that that second law that we're very familiar with, that the net force is equal to mass times acceleration. is really a special case. And we have to understand that that's a special case. So Newton actually postulated that a force applied to a body can change the magnitude of the momentum, or its direction, or both. So it can change. So if I apply a force on something, it can change its direction. It can change its momentum, or it could do both. I can have both a change in momentum and a change in direction. Think about that for a second. If my hockey puck hits the boards, the hockey puck's going to bounce off, and I get a change in motion and a change in direction. So let's define momentum, and we're going to start playing with momentum later on in the semester. But I really want to define it right now because momentum, and we usually use the letter P, it is a vector quantity. It has direction. It's a quantity of motion measured as a product of its mass times its velocity. All right? It's mass times its velocity. So we're going to define our symbol for force, and we're going to use force. It's a vector, okay? It's going to have direction and magnitude. And we want to look at how Newton postulated this. So Newton actually postulated that it was a change in momentum with respect to time, because my motion is with respect to time. So I can write this out here, that I get my change in momentum. All I'm doing is replacing P with respect to time. And when I do that, and I can do a mathematical trick, that I can look at the change in mass with respect to time times the velocity, plus the mass times the change in velocity with respect to time. It's called the chain rule if we're dealing with the calculus, and we're actually seeing it in the calculus, and I'm going to actually give you the calculus representation, but these two are essentially the same discussion, right? They're the same discussion. So in our normal day, let's look at what's happening here, okay? Let's look at what's happening here. If I'm dealing with a ball, and I'm dealing with, or that hockey puck that hits the boards and it comes back over it, the odds of it's changing its mass over any given time that we're dealing with it, it's not going to happen. It's not changing its mass. So what happens is this term right here, we can go ahead and exclude it in most cases. In most cases, we can do an exclusion. Let's go back. We can do an exclusion of this term. We can actually remove that term. So, but then I'm left with just this term right there. And we know what the change in velocity with respect to time is. That's acceleration. So most of the time, we can get rid of it, which gives us our special case of our net force is equal to the mass times the acceleration. Now, there are cases when I can't disregard that change in mass. Think of a rocket that's trying to go to the moon, or a rocket that's going to the space station, or if you remember the shuttle, when it first took off, it had 3 big, huge external tanks that were filled with fuel, those fuel was going off, and the shuttle was actually a much, much smaller part of it. It had a change in mass with respect to time. So I had to account for that thrust. I had to account for that change in mass. You can even think of it in terms of a car. Most of the time the weight of the fuel in the car is small compared to the overall weight of the car, so I can disregard that change in mass with respect to time component. So most of the time we can go with that common representation of my force is equal to my mass times my acceleration. But again, I want you to see this because Newton didn't actually say that. And how we actually go back to Newton's second law that we commonly use, because we're going to use this a lot and it works really, really well. But we need to make sure that we understand that there is this other term out there and that this is a special case. So Newton's law combines force and acceleration. So if I take force divided by acceleration, I'm going to get mass. So if I plot force versus acceleration, I'm going to get a straight line, and the slope of that line is going to be related to mass, the mass of the object. The more mass of the object I have, the bigger, the more force is going to have to be applied to get the same acceleration. And we can look at a box, and we talk about this being the sum of all of those vectors, those vector quantities. And when we start to do example problems, you'll be able to see that my net force is the sum of the forces. Think of about a tug-of-war situation. I have the flag in the middle, and if one side is applying a force of 10 newtons to the left, and the other side's applying a force of 5 newtons to the right, guess where the flag's going to move? It's going to move to the side that's applying more force. Since I had 10 applied to the left and 15 applied to the right, the flag's going to move with a force of 5 newtons to the right. I can do those kinds of problems, and we've done those kinds of problems in the past. We know that we can have it. So this is my inertial mass, the mass that's got there. This is the rate of change of the velocity. My force is going to be in the same direction as my acceleration, and we get our sum acting on the forces. I need to bring up another type of force at this point. We want to talk about Hooke's law, and we're going to bring in the idea of springs. So Newton's law says that the force is equal to mass times acceleration, but if I'm dealing with a spring, I get Hooke's law. And what we see is that when I deal with a spring, there's always trying to be a restoring force. It's trying to get to its normal condition. So that spring is going to apply, and Hooke actually showed us that it's a restoring force, which is why I get a negative here, because I'm restoring it to its original position, and I can utilize this with the spring constant K and the change in X, where the change in X is related to the stretch of my spring. So I've got my little IO lab here again, and I've set it up so that I've got the original spring in its original condition, and I've got the stretch string when I have the force that's being applied, and the force that's being applied in this case is the weight of my little IO lab. And we can actually calculate this spring constant. And the reason I bring that up is the spring constant is going to be dependent on the spring. So if I think if I have a slinky, it's going to have a different spring constant associated with it than I'm going to get with a spring that's around my shock absorber underneath the car, or the spring that's in my garage door that has my garage door opener, or the spring that's in, say, a stapler. All of those springs are going to have different spring constants. And those are going to be dependent on the material, the number of windings, a whole lot of traditional orientation type things, both the configuration and the material, that's related to the spring. So I have to measure those spring constants for each individual spring. And I can get that force. And this H is going to denote that it's a Hooke's law equation. So we can do it. I went out and I got the mass of my IO lab. It's 204 grams. My initial length of the spring was 6.3 centimeters. The stretched length of the spring was 18.2 centimeters. So the actual stretch of the spring related to that force that was being applied was 11.9 centimeters. So I'm going to do just the magnitude of my force, because remember that negative says it's a restoring force. It's trying to pull it back up. So it's a restoring force. So that negative is what's giving me direction. And I'm going to solve for K. So I get the magnitude of my force divided by the stretch of the spring. And I put in my mass, 0.204 kilograms, because I want to be in SI units. 9.8 meters per second squared, which is my acceleration due to gravity. And my 0.119 meters to come up with a spring constant of 16.8 Newton meters. Gives us a good time to look at our units of force. Now we could have looked at it back on our force as being our net force, but it's kind of nice to actually plug in numbers and see the unit analysis to get us there. But the units of force is going to be in Newton in the SI system. And that's going to give me my mass, which is in kilograms, my acceleration, which is in meters per second squared. So that's going to give me my force. It's also a good time to caution about the English system. A force in the English system is pounds. The acceleration is in feet per second squared. And remember, the acceleration in the English system is 32 feet per second squared. But that gives me this weird thing for mass. And we don't normally talk about mass in the English system, because we're always comparing things in pounds, right? We're talking about weights. We're not talking about mass. But when I go back and I actually look at it, the English unit for mass is a slug. So we actually do have an English unit for mass. So now we'll talk about Newton's third postulate, because all of these things are going to come together to allow us to work problems. So we've got the first postulate: an object in motion remains in motion, or an object at rest remains at rest unless acted upon by another force. We've got our special condition that we're going to utilize of Newton's second law, that the net forces, the sum of those vector forces, is going to equal the mass times the acceleration, and the force and the net force is going to be in the same direction as the acceleration. But we have the third one, and that is the postulate that when two bodies interact, they apply forces to one another that are equal in magnitude but opposite in direction. Think about that picture with Mark and Wilma. They were pushing on each other. So she was applying a force to Mark. Mark was applying a force to her. And if they didn't go anywhere, the forces that were being applied were equal but opposite. Similarly, if I have a person or this child standing on the earth, she's applying a force to the surface of the earth equal to her weight, but the earth is pushing back on her with a force that we're actually going to call a normal force that's equal to the magnitude of her weight, but it's in the opposite direction. Okay? So they're going back and forth. Well, similarly, if I look at the earth and the sun has a great big mass, right? The sun has a great big mass, and it's applying a force on the earth, and the earth's applying a force on the sun. And we're about to see that here in just a little bit. And this is where chapter 7 comes in. But the sun and the earth are actually pulling on each other in opposite directions. The sun is actually pulling on the earth, which is what's keeping us in orbit. But the sun is actually pulling on the earth's actually pulling on the sun a little bit. And we can know that for a fact because we see something that evidence of that here on Earth. For example, the moon actually pulls on the earth, and the earth pulls on the moon. And because the surface of the earth isn't firm, okay, it's not totally solid, what happens is when the earth rotates, the water gets pulled towards the moon, and then on the other side, it's not being pulled, it's still being pulled towards the moon, so I'm going to get tides as a result of that, what we call that gravitational pull between the moon and the earth. So, I want to take a step back for a moment, because really, where did these three postulates come from? Why was Newton even thinking about it, okay? And in your cool videos, there's the BBC idea of Newton, so you can go back and actually look at it and see how that worked. But let's think about why these three postulates came. Well, he was aware of work from other folks, okay? Brockie and Kepler. And what was happening was they were trying to explain, and so Newton was aware of Kepler's work, and Newton was trying to recreate Kepler's work with the Earth-Moon system, whereas Kepler was using Brockie's observational data to explain the orbits of the planets. So we've got a couple of different things that are happening. Newton had to come up with some postulates in order to think through these particular experiments, and what were they trying to do? You know, what was the thing that they were trying to do? And one of the things they were trying to do was explain the motion of Mars in the sky. And we call that retrograde. And basically what happens is if I watch Mars, and this happened in 2016, Mars goes across the sky and it looks like it does a little loop-de-loop and it goes out. And by the way, I just want to kind of point out, these are where I got these diagrams, so I'm giving attribution to the people who put these diagrams together. You can actually go to those links to see the rest of the articles there, but these are really good diagrams, and rather than try to recreate the wheel, I'm borrowing those diagrams with proper attribution so that we can have it look out there. So it gives us this little loop-de-loop. So what's happening here is let's start here. When I'm looking at Mars from this position, Mars appears in the sky over there. Now, as I start to move here, and as Mars is moving, remember the Earth's in a closer orbit, so it's going to move faster around the circle than Mars is. It's going to look like Mars is there in the sky. But once I pass Mars, look what happens. I end up with Mars looking like it's traveling backwards. And it's a relative motion problem, just like what we've seen before with velocity. It's a relative motion problem. And they were trying to explain this, explain that motion. So Kepler, in trying to explain this, came up with what we know of as Kepler's laws. And the first assumption that he makes is that the Earth, or that all orbits are going to be ellipses. And the sun is actually at one focus of the ellipse. And that turns out for Mercury, Venus, the Earth, and Mars, our ellipses are very, very circular. And remember that a circle is a special ellipse where both focuses are located at the same point. You can even go back and calculate it and see that the focus of our ellipse, the two foci of our ellipse, actually reside inside the diameter of the sun. If you want to play with the Earth's orbit, you can actually do that. But that's our first assumption. The second assumption that he said, or was able to show, was that as I swept through my particular orbit, that this time, the time that it takes to get from H to I, is the same time that it takes to get from I to J, which is the same time that it takes to get from G to H, that the areas of these triangles are going to be equal. And that's one of the calculations. You can actually go into Newton's notebooks with that link that I showed you and actually see Newton do these calculations to actually prove Kepler's law here, that the areas of those particular triangles or those wedges were identical, that swept out. And then finally, that as a nominal, that the period of the orbit was related to the axis of the orbit times some kind of constant. And you can actually go and verify that using Newton's law of universal gravitation, which is what he ultimately came up with by using those three postulates that we already have talked about, that Newton's going to actually derive his universal law of gravitation. So Kepler's empirical model used three laws to describe the orbits tracked by Brachii. Newton knew of Kepler's laws and tried to prove them mathematically and was able to do so. So that's where these things happen. So again, Newton was using the Earth-Moon system. And so he was saying, now remember that postulate that the masses are going to have an equal but opposite force applied to them. And by doing that and doing his thought experiment, he comes up with the universal law of gravitation. Now the negative there is that if I'm on the surface of the Earth, I'm being attracted to that point, that center of mass of the Earth, and so I'm going to be traveling in the negative R direction. If we think of R being moving away from the center of the Earth, that negative pulls us in. And he was able to say that we have some universal constant of gravitation, the mass 1, mass 2, divided by R squared. And this was ultimately proven experimentally by using the Cavendish apparatus. And in those Cool Force videos, you can actually see the Cavendish experiment. We can actually do it, and with lasers, it's much, much easier than the way Cavendish had to prove it. So we can get that. So let's look at this a little bit more. So we could do it with the sum of the individual masses, and this is another part where Newton helps derive calculus to help explain things, because we can look at each individual, we can divide up the Earth into a bunch of infinitesimal smaller masses and look at all of that and be able to show that the net source of all these masses is going to act at the center of mass. And we can get the resultant force that applies along a line between the two centers of mass, between the center of mass of the Earth and the center of mass of the Moon, if this were the Moon's case. And we can get this part there. So when we do this, one of the things that happens is we're going to have centripetal motion, or the motion, circular motion, and we'll see that here in just a second, and what's happening at the surface of the Earth. Now there is a slight variation in the acceleration due to gravity based on this, but for the most part, the change in radius of any object on the surface of the Earth is not going to be very, very big, so there's not going to be a big, huge change. Now, there might be a bigger, huge change as if I'm further away from the surface of the Earth, which is why I can be weightless or feel weightless, and then start to have this motion that's going to be our centripetal acceleration that we've seen and developed before, which is v squared over r. We can actually get that. But here, let's look at this being rewritten, the universal law of gravitation being rewritten for the Earth and an object on the Earth. So here's my gravitational constant, the mass of the Earth, the radius of the Earth, and we can see that the radius of the Earth isn't going to change very much. So it turns out that my acceleration due to gravity at the surface of the Earth is related to the mass of the Earth divided by the radius of the Earth squared, g, and that gives us our weight at the surface of the Earth. So F equal mg, or that weight, is a special case related to if I'm dealing with planetary motion because I am so close to the surface of the Earth. These two diagrams come from this particular website. There's another one that you might want to look at. These two diagrams come from our book, our text, and there's another particular website that you might want to look at. So now let's start applying this so that we can start working problems. So that's all the theory stuff, but we've got to start looking at how we're going to start working problems, how are we going to interpret things, how are we going to draw our pictures. And so we're going to start getting into free body diagrams, and I'm going to introduce another force just yet. So we know we have a push or a pull, so I have a crate here. We have this contact with the floor. We've already talked about that I'm going to have, using that third postulate, I get the weight of my block, or the weight of my crate is applying down. I get a force that's applying back up, which we're going to call the normal force. And we know that ultimately this person is going to be pulling this object down the road. We also know that depending on what surface that this person's pulling it on, it's going to also impact the amount of force that I have to apply. I also want to show this one as well. I've got the weight of my bananas being pulled down, but there's an equal but opposite force being applied by the rope, which we're going to call tension when we start working problems, that I'm going to get this tension going up the rope and I'm going to come down. And that's why we start talking about free body diagrams. So we're going to keep track of our systems by looking at what we call a free body diagram or a force body diagram. So let's look at what's happening on Mark. Mark and Wilma have a contact force here. So here's the force that Wilma is pushing off onto Mark. Now, even though we're on ice, there's going to be a force that we're going to call friction that's going to apply, and friction is a resistance to motion. So we've got a force due to friction, and this one's given with a subscript of a K, meaning kinetic friction. We have two types of friction. We all know that if I have an object, once I get it moving, it's a lot easier to keep it moving than trying to get it started, because there's a static friction as well. And you can look at the molecular kind of surface, and we know from experience that if I'm trying to pull a smooth object over gravel, it's going to be very different than if I'm trying to take that smooth object over a nicely treated thin plane of ice. So we know about friction, when friction sometimes is our friend and sometimes not our friend. Friction's our friend because it allows us to walk across the floor. It allows the car to move, so in that case it is our friend, but friction later on we'll see is not our friend, because friction can result in a loss of energy when we start doing our energy type analyses. We also have the weight of Mark being applied down, and then we have a normal force that's being applied up. And remember, we're going to have forces in two different dimensions, so that we're going to have to watch those dimensions and things are happening independently. And ultimately, if we get that push, he's going to move off in that direction, and I'm going to get an acceleration in that direction. So again, we're talking about that force due to friction. That friction force is going to resist motion, and I get a coefficient of friction That coefficient of friction is dependent on the two materials that I have. It comes up microscopically, and there are people that are out there measuring those coefficients. There's a different coefficient between rubber and ice, which is what I'm going to see with a hockey puck, versus wood on sandpaper, versus wood on wood, versus wood on steel. And there are tables of these coefficients of friction, or you'll be given these coefficients of friction as part of your problems to look at. And it turns out that the coefficient of or that the force due to friction is related to our coefficient due to friction times the normal force that's being applied, which is equal but opposite the weight that I have when I'm on a horizontal surface. And you can kind of remember this as friction is fun. We could do free body diagrams when we have pulley systems. One of the interesting things is if I have a rope that's connected, the tension in this part of the rope is going to equal the tension in that part of the rope. And I can look at the forces that are being applied on the cylinder, and I can look at the forces that are being applied on the cart. So I can draw my free body diagrams. So in chapter 5, we talk about gravity, we talk about Hooke's law, we talk about our normal forces, we talk about our tension forces, and we talk about our frictional forces. Now remember, even though in chapter 5 we haven't talked about static forces yet, and she's only bringing it out in terms of kinetic forces, to be able to calculate static force is the same way. Friction, or the force due to static friction is the big F, is equal to the coefficient of static friction times the normal force. And we can look at those things. So we can apply this to different models, right? Static friction, I can have my tennis shoe here and I can lift this particular plane and it's going to stay in its spot until the force due to gravity applied along this inclined plane exceeds the maximum force associated with the static friction. Because ultimately, as we move this up, the tennis shoe is going to slide down. Kinetic friction, we also can have rolling friction, and we won't necessarily work with that too much, but you want to be able to be aware that it is there, and we can use friction in a variety of ways. So when we start seeing those problems and those worked problems, you'll start seeing how friction is going to come into play. Remember, uniform circular motion requires something to provide a centripetal force. So if I've got the people in the round here, we can look at our normal force and gravitational force, and we've got our normal force against the wall, and it's related to that V squared over R. Again, I encourage you to look at the Pepsi Max video with the guy running the loop, because that's a nice particular part. So anytime I'm running around a curve, I'm going to get that center pull motion. So we can look at our free body diagrams for the tennis shoe on the system. I've told you before, we like inclined planes, and so we can write our different force diagrams for these inclined plane options. And then finally, our banked car turns. And we ended the last chapter with understanding we did that one problem where we did a flat curve, and I said, hey, this is going to become important when we start dealing with inclined planes. And we actually did that problem where we show that that inclined plane or that banked turn comes into play. And here's where we're going to see it again. So as we start applying these problems in these 3 chapters, you're going to have to be aware of those particular aspects. And we want to look at those changes that gives us our centripetal acceleration, which applies us towards the center of the circle. But if I don't have uniform circular motion, I'm going to get a tangential component. So as if I'm going through a turn, if I want to increase my velocity, guess what I'm going to have to do? I'm going to have to accelerate, and I'm going to get a tangential component for acceleration. So hopefully that